We have received two polymer samples. They have the same formulations, but they are different results. They are produced in 2 different days. One of them produces parts that are good. One of them produces parts that they crack during the assembly. They are used to make injection molding parts. We're going to use the instruments in the lab to identify what is causing that, what would cause one polymer sample to produce injection molding parts that they crack during assembly. One of the machines that we're going to use for unit root cause analysis is STA429. This machine has a GC mass, FTIR, DSC, and a TGA all combined together in one machine. It's a very advanced and very sensitive machine. Very good capability for doing thermal analysis, GC mass, and FTIR. At the same time, we'll look at deep into degradation of the materials. Another machine that we're going to use for this root cause analysis is strong, the thin cell machine, and we're going to make dog bone samples and we stretch it under controlled conditions to see what would be the response of the material to mechanical loading. One of the other machines that we're going to use for this root cause analysis is BDX7000. It's an X-ray machine, and it will shoot X-ray into the samples to identify the quantity of the additive inside the compound.
So STA testing is finished. This is a very important test for thermal stability checking of the materials. And the way that it works from left to right is that the material is heated with a rate of 10 degrees per minute. And about 7 minutes, we will see an endothermic peak that represents melting of HDPE. That's a sharp peak, and after HDPE is melted, we keep going until we reach 230 degrees centigrade. We'll keep the material for 5 minutes at that temperature, and then after that, we will insert oxygen at 27 minutes. When oxygen is inserted, the material will be exposed, and oxygen will start attacking the material. And oxidation would happen. Here, the role of thermal stabilizer become very important. What will happen is that when free radicals form as a result of oxygen attack, the thermal stabilizer would react with free radicals and basically blind those free radicals. So they prevent thermal oxidation to happen. You can see that for good resin, this would happen very good, and the oxidation is controlled. For bad resin, however, you can see at about 37 minutes we will see a peak. So that region is called oxidation induction time, and that means that after sometimes the bad resin or bad compound started to give up to oxidation reaction, and we will see an exothermic peak because the oxidation reaction is exothermic, and that peak shows that the bad compound doesn't have enough thermal stabilizer inside. That's why it's more prone to oxidation. And basically after that time, it's about 37-38 minutes, the test is finished and the cooling would start to be happening, and basically test is done. So these tests shows that the bad resin is already has experienced a compounding conditions that has consumed its thermal stabilizer. So so either there is not enough thermal stabilizer in the compound, or already the compound has been at the edge for thermal oxidation. The second test that is also very important for checking the degradation of the polymers is FTIR. We will look at the fingerprint area of HDP compounds, and we can see that for bad resin, we have significant peaks in carbonyl region. We have two peaks in those regions that are sign of oxidation. When oxidation happens, carbonyl groups will form and will result in formation of those peaks. We can further analyze this through peak feeding, so analyzing the individual peaks, calculating the area under the peak, and start quantifying the oxidation. But what it is clear is that the bad resin already has significant oxidation within it, even before putting it into the injection molding process. So this has to be carefully be monitored when this material is processed. Another test that we use to characterize these polymers is mechanical and its tensile stress testing. What will happen is that we will compression mold the samples, and we stretch it in a tensile machine, and we'll look at the tensile stress strain curve. As you can see, the good sample has significantly higher stress strain curve compared to the bad sample in terms of both yield stress, yield strain, and elongation. So looking at the curve, you can see that the oxidation for bad sample has already impacted the backbone of the polymers and has impacted the molecular weight of the resin. So if you use the bad sample to make injection molding parts, it would already has some degraded mechanical properties. So mechanical properties already poor compared to the good sample. Key takeaways from this root cause analysis is that so the first, we found that the HDPE resin or polymer was not a medical grade. When we are working in biomedical device industry, it's important to start with medical grade polymers. There are more controls over these material versus non-medical grade. The second was master batch compatibility. If you are using a compound that has a master batch, like a pigment, other colorant, and like that you want a certain color, make sure that there is compatibility between the base resin and the master batch resin. Like if you are using extrusion grade HDPE and your master batch is produced with the injection molding grade HDPE, there is a mismatch in rheology between the two polymers, and that would create problems for your compounding process. The very important thing is that the resin grade suitability. We found that the HDPE was extrusion grade and not suitable for injection molding grade. I mean, you can use it, but it's not the right resin for this. It has a high molecular weight distribution and is not intended for injection molding process. The other important factor that we noticed is that the barium sulfate loading. Although we did XRF testing and we found that the quantity of barium sulfate was very similar for both compounds, the 30% barium sulfate is high for polymers, especially for injection molding part. It could promote stress concentration, and that if you do accelerated aging at high temperature, it could create, it could promote cracking. So if you are adding a barium sulfate, just to make sure that you are adding it for the right cause and it's the level also is very important. Like there is a significant difference even between 20 to 30% loading of barium sulfate. And a very important, and the last one, is a storage at 60 degrees C. We found that these compounds are stored at 60 degrees C for some time, and also some of the parts are accelerated at 60 degrees C. When you are dealing with a fresh HDPE resin, there is enough antioxidant or thermal stabilizer inside the resin that would protect the material. I mean, there is always oxidation when parts are exposed to oxygen. There is oxidation, and based off the Arrhenius equation is just the reaction rate that is, small or smaller compared to when you are melting the polymers. But the oxidation is there. It's just that the antioxidant and thermal stabilizer that you have is protecting the resin. If those thermal stabilizer and antioxidant are already consumed and they are not there, the material is prone to oxidation. And even at 60 degrees C, if you increase the time, this could impact the backbones of the polymers, and it could impact the mechanical properties of the material. And that's a question that we always are, dealing with accelerated aging. Is that 60, storage at 60 degrees C would impact the polymers or not? So a test like oxidation induction time could determine how vulnerable is the material to oxidation.